going to speak about rational homotopy of embedding spaces. So, and indeed, my talk is in a way continuation of what Benoit was talking about. So, and it's also joint work with Benoit and Thomas. And I will actually speak about two rather unrelated stories. So the first story is about this Grothendieck-Teichmüller algebra, how it appears in the as a summand in the rational homotopy of long embedding spaces. And so somehow I found that like it's conference which is about GRT in the title, so I also thought that I would speak about this. It's a rather short story. And second, it will be about the rational homotopy type of embedding spaces and how unitrivalent graphs encode the certain invariants which in their turn encode the rational homotopy type of different components of embedding spaces. So, and I will start with the first story. So first story which where I really want to explain how this Grothendieck-Teichmüller algebra appears as a direct summand in the rational homotopy of embedding spaces, which is the same as the rational homotopy of the map of operats, right? So the Benoit was talking about that, right? We have the looping result, and because of this, the map of operats, rational homotopy of map of operats is the same as rational homotopy of disk embedding spaces. So second story, it's about invariance of zero in terms of unitrivalent graphs. So I will talk about this a little bit later. So the first story starts with the result that the rational homotopy can be computed by the hairy graph complex, right? So what Benoit was talking about. So there is this hairy graph complex which computes the rational homotopy. And on the other hand, we also have that we have natural inclusion map from the Kontsevich graph complex GCN to the hairy graph complex. So, and the idea of this map is just attachment of an edge. So given some graph, so we call them like bold graph. So it can go to the sum of the graphs where we attach to one of the vertices. We are attaching an edge, right? So we just take the sum of attachment of an edge like this. And so it turns out that this map is an inclusion, and actually what we have a map which goes the other way around. So it's actually a retract. GCN is a retract, and on the other hand, Thomas showed that in case n is even, the rational Grothendieck-Teichmüller algebra is part of the homology of this Kontsevich graph complex. And so we can see immediately that this summand also appears in the rational homotopy of embedding spaces, of disk embedding spaces, at least when k-dimension is at least 3. Right? So you remember that this theorem actually is when k-dimension is at least 3. So first it was proved for k-dimension in the case when spaces are connected, but then we improved it to k-dimension at least 3 using this looping result and then the rational homotopy theory of operats, which well, Benoit was talking about this proof. So let me give a little bit different algebraic description of this inclusion, which comes from the calculus viewpoint. So is there any question? No. Okay, so now I'm going to talk about very briefly about the calculus viewpoint. So Goodwillie calculus provides a tower of approximations of the space of embeddings, right, of the space that we have here, right? So we get a bunch of approximations, degree 0 approximations, degree 1, degree 2, and so on. And roughly speaking, so what these maps come from? They really come from evaluations. Maps, so given an embedding, we can get a map of configuration spaces, like I points in the first disk to the I points in the second disk, and this map are sigma I equivariant, and the case approximation is a certain space of maps of it's a subspace in the product. So roughly speaking, it's a subspace of the product of maps of configuration spaces. But to be precise, so this is just kind of intuitive description. But to be precise, it can be described as a map of I call them infinitesimal bimodals over the EM over the little disk operator from GM to GN. But now we take the truncated version. So we say that let's take sorry, it's not M. So just I can say it's a little disk operator. So M and N. But we take the truncated version, so which means that we restrict the cardinality of disk up to K. So essentially, any operator uses the structure of truncated operator, where we only care about RETK, right? So, and like topologically, it means that we need to care when points in the configurations in the disk collide. So we also want in the image that they should collide in DN, and this is really expressed in terms of operator maps. So it's really in terms of little disk operator. It describes how one should understand it. So, and moreover, we actually described a different complex. So we call it Causal graph complex, which also computes the rational homotopy of the little disk operator. So this is a graph complex. So it's not a graph complex; it's just a different complex, which also computes the homotopy groups of the space. And so it looks like this. So it starts with a really term of degree 2. So in degree 0 and 1, the homotopy groups of just one point in disk are trivial. So it really comes from 2. And advantage of this graph complex, it also can compute the rational homotopy of the stages of Goodwillie tower. So for example, if you want to compute the rational homotopy of D4, we just need to truncate up to term 4, right, and take the differential 0 from the last term. So this computes the rational homotopy of T4. DN. And also notice that the first possibly not trivial differential actually is trivial. So we see we have 0 here. Here we have 0, and therefore, if you want to compute the part of the homotopy groups which comes from this term, we really just need to compute the kernel of the differential of this map. So just to explain, what are these guys? So EM of M is a Causal dual of the homology of the little disk operator, so which is either Poisson operator or associative operator if M is 1. Also, more geometrically, every component here of this Causal dual operator can be described as a Borel-Moore homology. Homology of the configurations of configuration space of K points in Rm, or in other words, it's the reduced homology of the one-point compactification. So one-point compactification. Okay, and so if we look at this differential, so well, I forgot to say that the NPN in this complex is a reduced part of the rational homotopy of configuration space. So this is a Drinfeld-Connolly algebra. Drinfeld-Connolly algebra. And this is a normalized part. So a certain part where normalized part is the part which is the kernel of all projections so when we forget one of the points, we get natural projections, and so we want to take the part which is in the kernel of all these projection maps. And and even we actually get this GRT as a kernel of this map, right? And so it's really the part of the homology which is in this term. I should say that this D is really the pentagon relation. So pentagon relation is encoded by this differential. And we know that pentagon implies hexagon. And this really expresses that in the fact that we can replace the Poisson operand by its suboperand of Lie algebras. See, we take the suboperand of Lie algebras, so the homotopy are going to be concentrated in just this term. To be precise, this is a correct identity, and this is almost correct. So this is not exactly, so not almost. So these things are not exactly true. So there is one more class which appears when m is odd. So n is still even, m is odd. There is one more class which is correspond to tripod. But anyway, the most of the homology really comes from this class, and so roughly speaking, the this Grothendieck-Teichmüller Lie algebra comes from really configurations of 3 points in like mapping of 3 points from the disk GM to the 3 points configuration of 3 points in the disk GM, and the pentagon relations comes from looking at what happens at 4 points. So something which one would expect. So another remark is that you remember that our map of attachment of an edge was so if you look at this map GSCN to hairy graph complex, so the image is actually always in the graphs with one hair, right? And the homology of this one-haired part of hairy graph complex is a part which comes from this operand Lie M. That's exactly the part which comes from one hair, and as I said, actually it's so essentially we get that this is a GCN is a retract of the one-haired part, and the homology of GCN is actually a very small part of the homology even of the one-haired part of the hairy graph complex. And right, so this is somehow it's interesting, to see that Grothendieck-Teichmüller Lie algebra also appears at direct summit, in the rational homotopy. But perhaps more interesting question is to understand the GCN action on hairy graph complex. So it does act, and specifically, what is the geometric meaning of this action, and and some algebraic property of this action. So this would be interesting to study. So that's essentially it about the first story. So do you have any questions? Okay, good. So this is the end of the first story, and now let me move on to the second story of my talk, and so it will be about the unitrivalent graphs. How we can obtain invariance from unitrivalent graphs for high-dimensional embeddings. Okay, so we get that. So consider the following situation. So M is a submanifold of Rm, and we consider all possible situations where M is either compact submanifold, right? Or we can consider that M is a complement to a compact submanifold, or more generally to a compact subset. So it's a situation when M is a neighborhood of infinity. Or another situation when we look at a disjoint union of submanifolds where each component is either compact or it's some subspace in Rm, which like it should coincide with with this subspace of a big ball. So it's either compact or component goes to infinity as a Euclidean space. So it's not necessarily Euclidean space RMG, but it can be like other submanifold. But outside the compact ball, it's just RMG. And we allow actually components of different dimensions. So typical example would be when we consider the spaces of we'll look to spaces of string links, right? When M is a this thing, or we consider the spaces of spherical leaks. So where when is like this, but of course we can also mix those guys, and we can also consider M, for example, to be SM1 disjoint union with RM2. So we can mix guys, and also manifolds may have boundary. So we also allow manifolds with boundary. And so the problems that we are looking at is to understand the rational homotopy type of the space of embeddings, and specifically how this type depends on the component. So not only we want to understand the rational homotopy of just one component, but with all components. And we put restriction n minus m at least 2, so that the tower converges. Actually, we want that m has handle dimension less than m. So at most it will be m minus 1, so that the geometrical codimension is at least 3, and the calculus is applicable. So and to do this, we are going to construct certain Hairy graph complex infinity algebra. So let's first A be CDJ model of one-point compactification of M. So when we add one point at infinity, and A bar be augmentation ideal with respect to the base point, which is infinity. So with respect to this infinity point, we can take augmentation ideal, and so that's how we defined our A bar. And so in specific examples, when M is a disjoint union of planes, we get that A bar is a reduced homology of wedge of spheres, right? You see that this algebra has a trivial product, right? So it can also be written as a direct sum of algebras SMI. So it's direct sum of algebras, and so products are going to be trivial in this algebra. For the spheres, like when M is a SMG, so in this case, the A bar is going to be a homology of disjoint union of spheres. So it is right. So it's also the direct sum of algebras. But here the products are going to be non-trivial. So now we are going to define this Hairy graph complex infinity algebra. Right, so this is Hairy graph complex infinity algebra. Hairy complex infinity algebra. So the degree. So we consider we consider the Hairy graph. So like it was in the top of Benoit, with the difference that now the hairs are going to be labeled by the elements of our algebra A bar. So AI are going to belong to A bar. And the degree is computed as a number of edges times n minus 1 minus number of internal vertices times n, and minus the sum of degrees of hairs, sum of degrees of each label that we put in univalent vertices. So differential is going to be the sum of two things. So first it will be expansion of a vertex. So it's vertex expansion. And we always expand the internal vertices, right? So we don't expand the hairs, only the internal vertices. So it's standard thing for graph complexes, but there will be additional summand in the differential delta join. So what this delta join does, it's so given a graph with a bunch of hairs and different labels, 1, A2, etc. So the delta join takes the sum of all possible ways to join at least two hairs, and then so they join to one new vertex, and over here we write the product of all labels, each come as a result of the joining. And over here we keep the previous labels, so in the hairs which are not joined. So there could be more hairs, which are not joined. So we keep the same labels. So the L-infinity structure is defined in the same way as delta join. So for example, when we take the bracket of two graphs, gamma 1 and gamma 2, so what we do, we also take the sum of possible ways to join hairs from gamma 1 and gamma 2. So we take some subset of hairs from first one, non-empty subset, and also some non-empty subset from the second, and we also write here the product of labels that were joined. Just a second. So this is, and so high brackets are defined exactly the same way. And so now the theorem that we had with Benoit and Thomas was that in case n codimension is at least 2 and m is as above, so each component of this embedding space is nilpotent, right? It's very important so that we can use a rational homotopy theory, and has finitely generated homotopy groups. And moreover, the map from the embedding space to the rationalized version of the Goodwillie tower is finite to 1 on pi 0. So it's finite to 1 on pi 0. So this means that pre-image of any component is going to be only finitely many components. So it means that in particular that we will be able to construct finite to 1 invariant and rational equivalence on components and rational equivalence on components on components. So moreover, we actually were able to describe to compute this part. So also this thing can be expressed algebraically. And so our result says that this limit of the tower is expressed as a simplicial set of Murray-Cartan elements of this hairy graph complex L-infinity algebra. It's quite interesting that the result actually calls for n minus m at least 2, and actually m could possibly coincide with Rm. So in the previous theorem, we always assume that m is above and m is does not coincide with Rm. So, or if you want, we need to have codimension at least 3, right? If you want to study the space of long nodes, we need to have codimension at least 3. But when codimension is 2, we can still compute the limit of the tower. And as a corollary of these theorems, so first of all, we get that one has a finite to 1 invariant, from the set of connected components of embedded to the set of Murray-Cartan elements, right? This is exactly the set of connected components of the simplicial set, and this is just Murray-Cartan elements of the hairy graph complex in infinity algebra modulo the gauge equivalence. This is gauge equivalence. Gauge equivalence. And moreover, we can compute the rational homotopy groups of each component. And actually, we can determine the rational homotopy type of each component by just shifting the by just taking the twist of the hairy graph complex by the corresponding Murray-Cartan element. Right. And if we also additionally assume that m is doesn't coincide with Rm, So then we can describe this set of Murray-Cartan elements by means of unitrivalent trees. So we have unitrivalent trees of degree 0. And this really just follows from the degree reason. So essentially graphs which have loops, they just don't appear in this graph complex. Only graphs that don't have loops appear. And for such graphs, we know that the homology of graph complex is concentrated in the trees. So therefore, only unitrivalent trees of degree 0 will contribute to this, to this invariant. I somehow want to emphasize that what we get invariance not in a vector space, but rather in just a set. But still, it's going to be very interesting invariant. So let me speak a little bit about the specific example. And let's look first on the spaces of string links. Right, so we look at the embeddings of a bunch of straight lines to Rn. So we assume that outside the compact set, the maps, the embeddings are standard. So in this case, as we discussed before, the algebra is just the direct sum of reduced cohomology of Rmi. And this algebra has a trivial product. So product is trivial. Sorry, not RMI. This is SMI. SMI. And this algebra has a trivial product. So product is trivial. And as a result, this L-infinity algebra is abelian. So is abelian. So all L-infinity bracket and all higher brackets are just trivial, as well as delta join is also trivial. So you remember the delta join is addition to the differential, and it's also equal to 0. So, and in this case, we obtain that the set of so the invariants take place in the set of Murray-Cartan elements. And this is going to be just the degree 0 homology of the hairy graph complex. And this set can also be described as a set of unitrivalent trees of degree 0 modular IHX relations. So this set is just unitrivalent trees. Trees of degree 0 modular IHX relation. It's quite interesting that we actually thanks to Hafliger, we actually have description of the at least rationally of this group, a group of embeddings of string links. So let me state this statement here. So this is really a statement due to Hafliger from 60s. 68, and Polярнос and Hafod-Submany and I, we just interpreted this result, result of Hafliger. So let me say Polярnос and Hafod-Submany and myself. So we interpreted this result, probably it was 2008. So we interpreted this so by saying that when we take the pi 0 of spaces of string links, so first of all, it's going to form a group. So this is going to be a group due to Hafliger, and it's a finitely generated abelian group. And when we take it to the, so when we take it tethered to rational numbers, we get that this group is exactly the degree 0 homology of our hairy graph complex. So somehow, right, so kind of So it's interesting to see that we also recovered here the H0 of this Hairy graph complex, and so this is a space of unitrivalent trees of degree 0. However, I should kind of say as a caveat, in this talk, that we haven't proved yet that these Murray-Cartan elements are additive, so that our invariant to the set of Murray-Cartan elements is additive. So we have natural addition in pi 0 of string links. So it's abelian groups, but we haven't proved yet that this Murray-Cartan elements are also going to be added in this case. Well, just to give a few examples, if we have, this is a little bit more complicated example. Just a second. So just, I want to give, sorry, I need to go up. I didn't get enough space for myself. So just as example, for example, if you have in the Murray-Cartan element a graph like this, right? So pan 2. So a graph like this really corresponds to the linking number, right? So for example, when we have an embeddings of Rm M1, Rm2, Rm plus 1 plus M2 plus 1. So then we have a linking number, and coefficient in front of this graph corresponds to the linking number. So this one example. Another example is when we look at the Baromean rings. This is an example of spherical Baromean rings, but we can open them up and get Baromean rings of Baromean string rings. And they're defined by taking M1 times Rm2 times Rm3, right? And then we have this equation. So essentially it's going to be an embedding of component. One component has dimension M1 plus M2 minus 1, another component M2 plus M3 minus 1, and the third component of dimension M2 plus M3 minus 1. So so now let's look at the spherical leaks. So first thing what we have is that when codimension is at least 3, we have that the pi 0 of spherical links coincide with pi 0 of string link. So now if you look at the algebra A, we need to take the cohomology of the disjoint union of spheres, which is the direct sum of cohomologies of SMI. But we still get that the set of Murray-Cartan elements of Hairy graph complex in this case is also coincide with H0 with Hairy graph complex AN, and actually we get exactly the same space of unitrivalent trees. So unitrivalent trees of degree 0 modular IHX relation. Modular IHX relation. So somehow the degree 0 homology of this graph complex is going to be exactly the same as the degree 0 homology for the case of string links. And this is really by degree reason. So only the trees which are labeled by the cohomology, top cohomology classes of the spheres are going to contribute. So you see that for the cohomology sphere, we have one class in degree 0 and one class in degree mi. And if we have a class in degree 0, this graph doesn't appear in the so this class will not have. So we might have labels like omega 1, omega 2, and also 1, 1, say 1, 3. But if any of the labels is of degree 0, like 1, 1, 1 or 1, 3, then this graph doesn't appear in degree 0 and so cannot contribute to the Murray-Cartan elements. So only trees which are labeled by the top cohomology classes of spheres will contribute. Right, and actually I didn't finish this example. So in this case, this picture corresponds to the tripod graph. So we have a graph like this, and it attributes to this one. And the coefficient in front of this graph must correspond to Milnor invariant. So, and finally, let me speak about situation when we have codimension 2. So when we look at the long string links, right, when M is Rm and codimension is 2. So in this case, we still get so we can still compute the limit of the rational Goodwillie tower. This is rational Goodwillie tower. And we can still express it as a simplicial set of Murray-Cartan elements of the hairy graph complex. And the thing is that this guy is can also be described as a degree 0 homology of the hairy graph complex M plus 2. And so for M equals to 1, now this space is exactly the space of unitrivalent graphs modular IHX relation. So this is Barnatan space. Space of unitrivalent graphs. And we expect that the map from pi 0, the corresponding map from pi 0 of embeddings R to R3 to this space that we so this set of Murray-Cartan elements onto the relations, it's essentially logarithm of Kontsevich integral. So we expect it behaves like logarithm of the Kontsevich integral. Must behave as the log of Kontsevich integral. Right. So this means that it should be additive, right? So this invariant must be additive, and also it must be universal in Vassiliev invariant. So in case M at least 2, the set of so this space of the hairy graph complex is it's essentially one loop part of the hairy graph homology. So it's one loop part. This thing is this is H0, one loop part. So and this part is spanned by the graphs which we call hedgehogs. So the graphs which look like this. Right, and so we get that the invariant is that we obtain here is much weaker, but we also believe that but that's exactly the invariance which the type of invariance which we expect from the TQFT theorem, logic quantum field theorem. Invariance. So we expect, so we haven't proved it, but we expect these are also invariants which come from the theory. So they were studied by several people. Okay, so I think I'm done. So any questions?
There are any questions? No. Yeah, if not, let's thank Victor again.